Hello, and welcome. In this video, we're going to go over section 4.2 from the Lock 5 textbook, and this is measuring evidence with p-values. So we're kind of focusing on how do we answer questions using data. So take a question, does drinking tea boost your immune system? Now we need to make this a little bit more specific. And this study comes from a 2003 study done by the National Academy of the Sciences. So participants were randomized to drink 5 or 6 cups of either tea, black tea, or coffee every day for 2 weeks. So both drinks have caffeine, but tea has an extra ingredient, chemical. That's what's being tested with this experiment. And after 2 weeks, blood samples for all the participants were exposed to an antigen, and the production of an interferon gamma immune system response was measured. So basically, blood was taken after the 6 weeks from all these participants, and then their blood was measured to see how it dealt with an antigen. So the explanatory variable in this experiment is whether the participants drank tea or coffee. The response variable is their immune system response on their blood. So does drinking tea actually boost your immunity? So if the tea drinkers have enough higher levels of immune system response, can we conclude that drinking tea rather than coffee caused an increase in this aspect of the immune response? And the answer is, of course, it's actually yes. Why is it yes? Normally this is always no. I always say no. The causation is difficult. But we're doing a randomized experiment which does allow conclusions about causality, since we're randomly assigning these two groups to drink the tea or the coffee. So let's set up our hypotheses. Mu subscript T is the mean immune system response after drinking tea, and the mu subscript C is the mean immune response after drinking coffee. So think about these are the two groups that the experiment split up. Does drinking tea boost immunity? All right, so right away before we get to the answer, we can cross off 2 of these 5 that absolutely cannot be correct. So can you see which of these 2 hypotheses absolutely can't be correct? And that is A and B. A and B cannot be correct because the null hypothesis has to be a statement of equality. So just looking at the null hypothesis, the answer could be C, D, or E. So we can cross off A and B right away. But now when you look at the alternative hypothesis, the evidence, or at least the question, is that drinking tea should have a higher mean response than coffee. So out of the choices C, D, and E, the answer is C, that tea is going to have a higher average response than coffee. So the explanatory variable is tea or coffee. The response variable is the immune system response. Measure the amount of interferon gamma produced. How would we visualize this data? Kind of going back to a chapter 2 content. And we do have 2 variables. So a lot of students would think scatterplot, but it's not scatterplot because we don't have 2 quantitative variables. We have 1 categorical variable and 1 quantitative variable. So we'd want to do a side-by-side box plot. Histogram works only for 1 variable. We have 2 variables, and then we want to do a box or bar chart in this case because that's for 1 variable also. We want a side-by-side box plot. And here's an example from 1 sample of this experiment. Here we have the immune response by the coffee drinkers, and then the 1 response by the tea drinkers. So notice the 2 categorical variables are split up into 2 box plots, and each box plot represents the quantitative variable immune response. So at least from this visualization, the tea drinkers have a higher immune response. Their median's close to 50, and the coffee median is close to maybe 15 or so. But the average is not shown on here. The average for the tea drinkers is 34.82, right around here. And the average for the coffee drinkers is 17.78. So the difference between the 2 samples is 17.12. So what might be happening? Why do the tea drinkers have a higher level of immune system response? Well, there's kind of two explanations I want to go through. The alternative hypothesis is true, that tea drinkers actually do get a higher immune system response than coffee drinkers. So tea is better than coffee in terms of this immune response. The second explanation B is that the null hypothesis is true, and we got this one sample by random chance. That people who got randomly assigned to the tea group have better immune systems than those who got randomly assigned to the coffee group. So this is possible. There's a random assignment, flipping coins, picking numbers to assign the two groups. It could just be the tea group had better immune systems and that the tea had nothing to do with it. So these are kind of the two options here. So the plausibility of the null. The goal is to determine whether the null hypothesis and random chance are a plausible explanation. Is that, let me go back here, that second response, the second explanation, is this possible? So we want to figure out, well, what kind of statistics might we get just by random chance if the null hypothesis were true? So we're going to take a conditional statement if the null hypothesis is true. And what we're going to do with this is do a simulation. So this was the actual experiment. We had a bunch of people randomly assigned to the two groups. So you're flipping a coin, drawing numbers, drawing cards, some way to randomly assign these two groups. And then the tea group drinks the tea for 2 weeks. The coffee group drinks coffee for the couple of weeks. That's conducting experiment. Measure the response variable, so they test the blood of all these participants after a couple of weeks. And then measure the response variable, and measure their immune. So here's the coffee group data and the tea group data. So we calculate a statistic. The tea average was about 38, and the coffee average was 17. So the difference between those two was about 17. So what we want to know is, well, this is definitely higher. The tea group got a significantly higher immune response variable on average, but is it higher enough, or could it be due to random chance? So does the tea boost immunity, or is this just a random chance experiment? There's always random chance, but we want to put a measure on this random chance. Okay. So how we're going to do this in chapter 4 is with simulations. So what we're going to do is take those two groups, and go back, and put them all together. Put them all together as one group. So this is all the data for the tea group and the coffee group, put as one group, and then we're randomly going to shuffle or reassign these into the two groups. So this is just purely random. Again, flipping coins, drawing cards, computer simulations. And we're going to get two different groups. So now it's not really tea, not really coffee. These are both groups put together. And then we're going to calculate the statistic, the difference between these two random groups. And in this case, we get a negative value because this random distribution of the coffee drinkers have a higher immune response. And we're going to repeat this many times using a technology such as StatKey. Ideally, we'll repeat this at least 1,000, maybe 2,000 times. So here would be the computer doing that simulation over and over again, 1,000 different times, and plotting out all the differences. So up here in the original sample, the difference was 17.12. It was reshuffled 1,000 different times, and each difference was plotted. So that last sample we just went through had a -12, so right around here. And the sample that we got, or the experimental sample, 17.12, that'd be right around this spot, 17.17. So the question is, how extreme is that observed statistic? And could we put a number? Could we talk about what we mean by extreme? Is the null hypothesis a plausible explanation? Could the null actually equal 0? Or maybe the null is not 0? And we won't be able to answer this question quite yet, but in the next video, later in the slides, we're going to talk about how we could use this simulation to get a plausible explanation that will convince you to reject the null hypothesis, that the null cannot be 0.